Okay. Yeah, so we are starting now. It looks like it's recording. So today we will review asymptotic complexity analysis. We'll just go through some examples of asymptotic complexity and how we analyze the asymptotic complexity of a given piece of code. And then we'll start discussing Mergesort. Okay, so most of this is going to be review material for most of you, but there will be a homework on this. So, and it's a homework on review material basically, but I wanted to make sure that everyone understands the basic rules for asymptotic complexity. For example, if we have this piece of code, I equals 3, I less than or equal n, I plus plus, and then you have some code here. Then, no matter where we start from, so regardless of the starting point here, whether this is a 3 or a 4 or a 5, then the running time of this is going to be what? So this is theta of n. This is theta of n. So even if this is, whether this is 3 or 5 or 6, it will still be theta of n because what? So what's the difference between 3 and 5? Constant. So as long as the difference is a constant, we don't care for asymptotic complexity. Why? Because n is going to be very large. Remember, with asymptotic complexity, n is going to be large, and mathematically it's going to go to infinity, which means that any constant here will be negligible compared to a large number. Okay? So now if we have something like, so this is theta of n. What if we have something like I less than or equal 2 times n? What will be the asymptotic complexity? Yeah, still theta of n, because now we are multiplying by 2. So this is the this is the bound of the loop. Bound. So we are increasing the bound by, we are multiplying the bound by 2, so we are still theta of n. Okay? So, but what if we do, so this is theta of n. Now what if we do I less than or equal n I times equal 2. And let's start from 1. So what's the running time now? What's the asymptotic complexity?
Log n.
So why is it log n?
Because
yes, go ahead.
Because every time it divides the number of steps, the stepping is increased by 2 every time.
Okay, so the stepping is so what's the difference between this and for I equals 1, I less than or equal n, I plus equals 2, and there is some operation here. So what's the difference? So this is, you're saying that this is theta log n, right?
Yes.
And this?
This is theta.
This is theta of n or log n?
That's n.
Yeah. Well, so this is, it's n over 2, but we ignore constants, right? So this is theta of n still, because we ignore constants. Now remember that this means that you start from 1 and you have this n, and then your steps are, so you start at 1, then 3, then 5, then 7. So you have a constant step, and this constant step is gonna only make it half the number of iterations is going to be half the number of iterations if this compared to the number of iterations if this was only 1. Okay, so this will only half the number of iterations. While here, so here we have this. So first we do 1, then 2, then 4, then 8, then 16, and so forth. So now the step here is not a constant step. The step is getting bigger and bigger. In fact, here our step is growing exponentially, which means that the number of steps is going to be logarithmic. So to just better understand this, because this is very important. So for n equals 16, suppose that n equals 16, the loop will get executed for I equals 1, and for I equals 2, for I equals 4, for I equals 8, and for I equals 16. So, or maybe we can just draw a table. So n and number of executions, loop executions, how many times the loop will get executed. So if n is 1, then the loop would get executed once. If n is 2, the loop will get executed twice. Now let's look only at values of n that are power of 2. Then we'll talk about what will happen if n is not a power of 2. But for power of 2, if n is 4, then how many times will the loop get executed? 3 times. And if n is 8, then this is going to be 4. And if n is 16, this is going to be 5. So the number of loop executions is the number of times this will get executed, which is the asymptotic complexity of the algorithm. It's how many times this operation will get executed. And what's the mathematical relation here? The mathematical relation between the number of loop executions and n is what?
2 raised to
2 raised to number of 2.
So number of loop executions. So if you call this x, then x equals what? What's the relation? What's x as a function of n? Is it log n?
Log n divided by 2.
Yeah, it's log n base 2 plus 1. So log 1 is 0 plus 1 is 1. Log 2 is 1 plus 1 is 2. Log 4 is 2 plus 1 is 3. Log 8 is 3 plus 1 is 4. So x, this, call it x. This is x. X, which is the number of times. X is number of times op is executed. So the number of times x is executed, the op is executed, is log n plus 1. But we don't care about plus 1 in the asymptotic complexity. So we say that the asymptotic complexity is theta log n. Now when we say it's theta log n, will it be important in asymptotic notation to specify the base? To say that it's log n base 2? So, okay, so the answer is no. It's not important to specify the base. Why?
It's a constant.
What do you mean it's a constant?
Log n to the base 2 is log n upon log 2, and log 2 is a constant. That would be to the base e.
Okay. It's last time we looked at a formula that converts from one base to another by multiplying by a constant. So remember the formula from last time. Log x base a equals log x base b divided by log a base b. So you can do the conversion. So for example, log n base 2, to find the relation between log n base 2 and log n base 10, say, it's going to be log n base 10 divided by log 2 base 10. And log 2 base 10 is a constant. Okay. So since we can convert from one base to another by multiplying by a constant, we don't need to specify the base in asymptotic notation because they're all of the same order. All logarithms are of the same order. Okay, so so this is for logarithmic. So remember that if you have a multiplication like this in the step of the loop, then this will lead to logarithmic running time. While if you have, for example, something like 2 times n here, this will still be theta n, right? Theta of n. So this is not the step. This is the bound. So multiplying the bound by 2 will only multiply the number of operations by a constant. So the multiplication here is different from the multiplication here. Okay. Okay. So now let's do some loop nesting. So if we do so the simple loop nesting, I less than or equal n, I plus plus, and for j equals 1, j less than or equal n, j less than or equal n, j plus plus, and we have an operation here. Then what's the running time?
N squared.
So this is n squared. This is theta of n squared. Now, is it true that whenever we have a nested loop, the asymptotic complexity is going to be n squared? No? Okay, so give me an example where we have a nested loop and...
Last time in the sorting, because it's all depend upon operation.
Okay.
Condition.
Oh, but you mean insertion sort?
Yeah. Yes.
But the example that we had in insertion sort, it ended up being n squared as well.
What if we break in the operation?
What if what?
Break.
If there is a break?
Yeah.
Well, even if, when you say, okay, if some condition, do the operation, else break. So how would you analyze this?
No, it will still go in the...
So it will still be n squared. Why? Because we do the worst case, right? We focus on the worst case. By the way, in this course, if we don't specify, whether we are interested in the best case or worst case or average case, we haven't even mentioned average case yet. But if we don't specify, then by default, we are interested in the worst case. By default, we are interested in doing the worst case analysis. And in this case, the worst case is that the condition will always be true, and this will get executed. So this is theta of n squared. But it's not true that whenever we have a nested loop, we have n squared. Can you think of an example where we have a nested loop, but it's not n squared? Yes?
If the inner loop only loops a constant amount of time.
Yeah, exactly. So what if we change this n to some constant like 10? then, yeah, so then in this case, this is theta of n. This loop by itself is theta of n, and this loop by itself is theta of 1. And then the overall t of n equals the multiplication of the two, theta of n multiplied by theta of 1, and this is theta of n. By the way, here, this is how I would like you to do the analysis. You know, when we analyze code like this, we will just analyze each loop individually, each loop separately, and then we indicate, you know, whether the relation is multiplication or addition or whatever. So in this case, it's theta of n, not necessarily n squared. Now, can you give me an example of a nested loop where the asymptotic complexity is more than n squared? A nested loop in which the asymptotic complexity is more than n squared.
Three loops.
What's that?
3 for the
No,
The limit,
only doubly nested loop. So a doubly nested loop,
the nested loop has the limit of n square, then it would be.
yeah, exactly. So this is n, but what if we do this, what if we change this to n, and we change this, or, okay. So let's change this I plus, let's keep this at n, and this is n times n, j plus plus. Now, in this case, the outer loop is theta of n by itself, and the inner loop is n squared by itself, and the total is going to be theta n times theta of n squared. So this is theta of n cubed. Okay, so if the inner loop has, or if one of the loops has more than n, then we may end up with n cubed. So it's not true that every doubly nested loop has an n squared running time. Okay, now what about this? For I equals 0, or I equals 1, I less than or equal n, I plus plus. For j equals I, j less than or equal I plus 3, j plus plus, and we have an operation. Now, what's the asymptotic complexity in this case? And why is it n?
Because j is equal to I.
They execute only thrice for every I is equals to.
Yeah, exactly. So the number of executions of the inner loop is going to be constant because we always go from I to I plus 3. So I to I plus 3, no matter what I is, we're going to do 4 times, in fact, because we go from I plus 0, I plus 0, I plus 1, I plus 2, I plus 3. So we'll do it 4 times. So the inner loop is executed 4 times. The outer loop is executed n times. So this is
4n.
theta of n. This is theta of 4, but theta of 4 is theta of 1. You know, 1 and 4 are of the same order because they're all constants. All constants are of the same order. So this is theta of 1. So the overall running time, t of n equals theta of n multiplied by theta of 1, and that gives theta of n. Okay. So yes.
In this example, if we do j equals j into 2, what will be the time complexity?
J?
Yeah, j equals j into 2.
Oh, multiplied by 2?
Log n.
Okay.
Log.
Yeah, so j multiplied by 2. Okay. So what will you get in this case? So it's basically, this is n squared log n squared base 2. Log n squared base 2. And what's this? Yeah, this is so log n squared base 2 is 2 log n base 2. So this is theta of log n. What does it mean? It means that even if this is n squared, because of the fast step, it will still be logarithmic. So log n squared and log n are of the same asymptotic complexity, because this is just moving the constant in front of the n, the log n. So log n squared with the n being squared is different from log n squared. So this is, you are squaring the whole thing, right? Or sometimes they write log squared n. So this is different. So here we are only squaring the n, and this will just be the same as log n asymptotically. Okay, so let's do one more example on a composite, on a loop that has an example that has multiple loops. Okay, what if we have this j less than or equal n, j plus equals 5, and then we have an operation, and then we have for k equals 1, k less than or equal n divided by 2, k plus plus, and we have an operation. So in this case, how do we analyze this? So don't give me the answer, just tell me how to analyze it, how to go by analyzing these, how to handle these three.
Separate both the loops, like handle both the loops separately. So we'll calculate the complexity for the first nested loop and then for the second one.
Yeah, exactly. So yeah, exactly. So the first so this is one. So this is a separate loop than this. So we have two separate loops. So the relation between this and this is going to be addition. So we analyze this and analyze this, and we add the asymptotic complexities. But these, since these are nested, we multiply them. So basically, this by itself is theta n, and this by itself is also theta n. So the relation between these two is multiply. And here, what's this? This is also n. So this is theta n, but we add it. So T of n equals theta of n times theta of n plus theta of n. And what's this?
2n squared.
Yeah, this is theta n squared. Because this is going to get neglected. This is a lower order term. So the idea here is that if you have separate loops, you add them. You analyze each loop separately, and you add the asymptotic complexities if they are separate loops or independent loops. But if there are nested loops, then you multiply. Of course, you multiply only if multiplication will not always be the solution, because as we have seen in insertion sort, if the number of executions of the inner loop is not always the same, then we'll have to do a summation like we did with insertion sort. But here, the number of executions of the inner loop is always the same. It's always n, or in fact here it's n over 5. N over 5 is asymptotically n. So we multiply. Okay, so you multiply only if the inner loop always has the same number of executions. Okay? All right, so this is basically a review to make sure that everyone knows these basics of algorithm analysis. Of course, in this course, we will be analyzing more complex algorithms. So there will be more interesting algorithms, and we will be learning more rules and more techniques for analyzing algorithms throughout this course. Okay. So I just wanted to go through these basics because there is a homework coming up on these basics. In the homework, there are also questions. There are questions that ask you to do some kind of calculation. So, for example, given an algorithm with an asymptotic complexity of theta of n squared, or consider an algorithm with an asymptotic complexity of n squared if the algorithm takes 3 seconds to process an input of size 10 power 4, how much time will it take to process an input of size 10 power 5? So what's the answer here? So it takes 3 seconds to process an input of size 10 power 4. How much time will it take to process an input of size 10 power 5? 30 seconds? Well, this is not true. So this is a common mistake. So this is the mistake. This is exactly why we have this question, to avoid making this mistake. So here, this answer implies, what does this answer imply? When you say 30 seconds, so the answer will be 30 seconds under what condition? If the algorithm is theta of n. So when you just do proportionality, you are implying that it's a theta of n algorithm. Proportionality is true only if the algorithm is linear. It's a linear time algorithm. But this is not a linear time algorithm. This is a it's a quadratic time algorithm. So what should we do? Of course we can do, because it's a quadratic time algorithm, so the quick solution is we multiplied the input, got 10 times larger. If the input got 10 times larger, then the processing time is going to be 100 times more, not 10 times more, because it's quadratic. But let's do it in more detail so that we can have a formula that we can apply to all kinds of algorithms. So let's use this formula. Time equals number of operations divided by speed. Now the machine speed here is not specified. Of course, it's implied here that it's on the same machine, on the same. If the question is not telling you whether it's the same machine or not, you should assume that it's the same machine, because it's not giving you any information about another machine and how much faster. So time equals number of operations divided by speed. So we can say that time 1 equals n1 squared divided by speed, and time 2 equals n2 squared by speed. This is equation 1. This is equation 2. So dividing 2 by 1, we get, what do we get if we divide 2 by 1? We get time 2 divided by time 1 equals n2 squared divided by n1 squared, right? Which is equal to n2 divided by n1, everything squared. And in this example, or in other words, time 2 equals time 1 multiplied by n2 divided by n1 squared. So in this case, time 1 is 3 times n2 divided by n1 is 10 power 5 divided by 10 power 4 squared. So this is going to be 300. Seconds. Like I said, we could have figured this out, quickly. We are multiplying the input by 10. It's quadratic. It's a quadratic function. So the running time will get multiplied by the square of 10, which is 100. Okay, but it's good to use this formula in general, and in the exams, it's a good idea to show your work, to show the steps, so that I know that you are not guessing. Okay. Okay. So in okay. And the third kind of questions that you will see in the homework is this. Given two functions, f of n, say equals n squared plus n plus 5, and g of n equals 5n cubed plus 2. So in this question, first indicate which one of these two functions is faster, asymptotically faster. So which one is asymptotically faster? Yeah, g of n is faster asymptotically. Then compare them using all the asymptotic notations that apply, and only give the asymptotic notations in which f of n appears on the left-hand side. So all the asymptotic notations that apply are, the most precise one here is what?
Theta.
F of n is, f of n is smaller. Remember, theta is equal, big O is less than or equal, big omega greater than or equal, small o is less than. small omega is greater than. So in this case, f of n is smaller, so you want to say small o of g of n. But also, the big O applies. F of n equals big O of g of n. And that's all what applies. So you only need to give all the asymptotic notations that apply, but with f of n appearing on the left-hand side of the equality. Okay? Okay, so this should prepare you for the first assignment. So let me now talk about Mergesort. Any questions before we start talking about Mergesort? Yes.
So when we say g of n is faster, we mean that g of n is faster in terms of the growing size?
Yeah, because in fact we're talking about functions here. We're not talking about algorithms. So yeah, so we're comparing functions. So you can say f of n is larger. That's less ambiguous. It's clear. You know, it's asymptotically larger. Asymptotically larger. So this is in English, and this is the mathematical way of expressing this. But make sure that you give both. You express it in English and in asymptotic notation, so that I know that you understand what the asymptotic notation means.